Welcome to Astral Quantum, the channel where we explore the unfathomable wonders of quantum physics and the universe itself. Here, we don't just look at the stars or imagine the cosmos, we dive deep into the very fabric of reality. Together, we'll uncover the strange, invisible forces that govern the smallest particles of matter, and perhaps even the deepest questions about existence itself. This isn't just a science lesson. It's a journey into the unknown, where the rules of the universe are far stranger than we could ever have imagined. You may be wondering, why quantum physics? What makes this particular field of science so captivating, and, dare I say, so important? The answer, in short, is everything. Quantum physics is the language that explains how the universe works on its most fundamental level. It's the foundation of all modern technology, the key to understanding the mysteries of space, time, and even consciousness itself. Whether we're talking about the light that powers your smartphone, the electricity that runs your fridge, or the very nature of existence, quantum physics plays a role. But don't be fooled. The quantum world isn't just about particles and equations. It's about something much deeper, our place in the universe. What happens when we truly begin to understand that the universe isn't just a vast, empty space full of things, but a vast, interconnected web of possibilities, of energy, of uncertainty, and yes, of mystery? For centuries, the universe was understood through classical physics, the physics that governed the world of Isaac Newton. In this world, everything is predictable. If you know the position and velocity of an object, you can tell exactly where it will be in the future. This deterministic view of the universe gave us the Industrial Revolution, the understanding of gravity, the motion of planets, and countless other scientific breakthroughs. But as we peered deeper into the microscopic world, things started to change. Classical physics could explain the behavior of large objects, like planets, cars, and buildings, but when it came to the smallest scales, atoms, electrons, photons, it began to fall short. Objects in the quantum world didn't behave like predictable machines. They were strange, unpredictable, and full of possibilities. In the early 20th century, scientists like Max Planck and Albert Einstein noticed something strange about light. They realized that light wasn't just a wave, as had been previously believed. It also behaved like a particle. This wasn't just a minor tweak to our understanding of light. It shattered the very idea of classical physics. Light, and by extension all matter, could be both a particle and a wave. This is known as wave-particle duality, and it marked the birth of quantum mechanics. So, what exactly is quantum physics? Simply put, it's the study of the smallest particles of the universe, things like electrons, protons, photons, and even smaller quantum fields that make up all matter. But quantum physics isn't just about these tiny building blocks. It's about the behavior of these particles. The rules governing them are radically different from the ones that apply to our everyday world. For example, quantum mechanics tells us that particles don't exist in one specific location, like a little marble rolling through space. Instead, they exist as probabilities, a cloud of potential locations, all at once. The more we try to measure where a particle is, the less certain we are about where it might be. In other words, the act of observation itself affects the outcome. This is known as the Heisenberg uncertainty principle, and it shows us that the very act of looking at something changes what we see. It's a world where certainty is replaced by probability, and where observation can alter reality itself. Now, you might be thinking, okay, this is all fascinating, but why does it matter to me? The answer is simple. Quantum mechanics governs the technology you use every day. Your smartphone, your computer, the internet, and even medical imaging all rely on the principles of quantum physics. Without quantum mechanics, the world as we know it today wouldn't be possible. Quantum computing, for example, is a cutting-edge field that promises to revolutionize the way we process information. Instead of using classical bits, which are either 0 or 1, quantum computers use qubits, quantum bits, that can exist in a superposition of both 0 and 1 at the same time. This means quantum computers can solve certain problems exponentially faster than traditional computers. Think about the potential impact on everything from cryptography to drug discovery to artificial intelligence. But quantum physics isn't just about technology. It's about understanding the very nature of reality itself. Quantum mechanics is challenging our deepest assumptions about the universe, about the relationship between the observer and the observed, about the nature of time and space, and even about consciousness. As we push the boundaries of what we know, we're faced with profound questions. Is the universe deterministic, or is it inherently random? Do parallel universes exist? Can time flow backward? And that's what makes quantum physics so exciting. It's not just about discovering how things work. It's about discovering how everything works. It's about peering into the very fabric of reality, at the smallest scale, and asking, what is really going on here? Quantum physics challenges our ideas of what is possible and forces us to rethink our place in the cosmos. So, if you're ready to leave the comfortable, predictable world behind and step into the wild, unpredictable realm of quantum physics, then you're in the right place. Together, we'll explore all these questions and more. We'll delve into the deep, sometimes paradoxical, nature of quantum reality. Whether we're exploring the many worlds interpretation, quantum entanglement, or quantum computing, one thing is certain: the journey will be fascinating. Stay tuned, because this is only the beginning. Over the course of this journey, we'll see how quantum physics doesn't just explain how things work, it transforms the way we think about everything. From the smallest particles to the vastest galaxies, the quantum world holds secrets that could change the way we understand ourselves and the universe forever. Welcome again to Astral Quantum, where the strange and beautiful universe of quantum physics comes alive. Let's dive deeper now into one of the most fundamental mysteries of the quantum world: wave-particle duality. The idea that particles, the building blocks of everything, can behave both as waves and as particles at the same time. It's a concept so strange that it makes you question everything you thought you knew about the universe. Imagine this: the very thing that makes up your body, the air around you, the stars in the sky, is made of tiny particles that don't just exist as solid objects, but also exist as waves, moving through space, vibrating, oscillating. And these waves aren't just waves in water, or sound waves traveling through air. They're waves in probability, in potential outcomes. The world at the quantum level doesn't behave the way we expect. Wave-particle duality first appeared in a famous experiment with light. You probably know light as something that enables us to see, something that travels in a straight line from point A to point B. But in the early 20th century, scientists discovered that light, when it passed through narrow slits, created an interference pattern, a series of light and dark bands, like ripples on the surface of water. This pattern suggested that light wasn't just a stream of particles, as many had assumed. It was also a wave. But that's not where the story ends. If you shine light at the slits one photon at a time, you still get the same interference pattern, as if the photon was somehow going through both slits at once, like a wave. This result was a major puzzle. If a photon is a particle, how could it act like a wave? The more scientists dug into this, the stranger things got. The same could be said for electrons, which are, of course, particles. Yet when scientists passed electrons through a similar experiment, they too displayed wave-like behavior. This is what we call wave-particle duality, the idea that particles like photons, electrons, and even atoms sometimes behave as particles, and at other times as waves. This idea shook the very foundation of physics. After all, how could something be two things at once? How could an object that we think of as solid and discrete, like a particle, also spread out like a wave? But as mind-bending as this sounds, it's been confirmed through numerous experiments, and it's one of the cornerstones of quantum physics. In fact, the weirdness of wave-particle duality leads us to some of the most puzzling concepts in quantum mechanics, like the famous double-slit experiment. You've probably heard of the double-slit experiment. It's one of the most iconic experiments in physics, and it shows us just how bizarre quantum mechanics really is. Here's how it goes. Imagine you're shooting tiny particles, like photons or electrons, at a barrier with two slits. Behind the barrier is a screen that will capture where the particles land. If you shoot the particles through the slits without observing them, you'll see an interference pattern on the screen, a series of bright and dark bands, just like the ones you'd see if you were observing waves. It's as if the particles are behaving like waves, spreading out through both slits at once and interfering with themselves. But here's where things get even stranger. If you put detectors in place to figure out which slit the particles are going through, the interference pattern disappears. The particles behave like particles again, landing on the screen as though they had chosen one slit or the other, not both. It's as if the mere act of observation forces them to make a decision. This is known as wave function collapse, and it's one of the most perplexing phenomena in quantum mechanics. So, what does this mean? It suggests that in the quantum world, particles don't have definite positions or properties until they're observed. They exist in a superposition, a mix of all possible states, until measurement forces them to choose one. It's as if the universe is filled with probabilities, waiting to be collapsed into reality by observation. It's a strange, counterintuitive idea, but it's backed up by countless experiments. The particles don't decide where they are until we look at them. And this brings us to a major question. Does reality exist independent of observation? This idea has led to some truly wild theories in quantum mechanics. One of the most famous is the many-worlds interpretation. According to this theory, when a quantum event occurs, all possible outcomes happen simultaneously, but in different, parallel realities. Every time a particle is measured, the universe splits into multiple branches, each representing a different outcome. In one branch, the particle goes through one slit. In another branch, it goes through the other. In this view, there are no probabilities, just different versions of reality. But that's not the only interpretation of wave-particle duality. Another, known as the Copenhagen interpretation, suggests that the wave function collapses when we observe it, and the particle takes on a definite state. This is the view most people are familiar with, and it's what most quantum physicists are taught. But as you can see, there's no consensus on what wave-particle duality really means. The interpretation of quantum mechanics is still one of the most hotly debated topics in the field. What we can say with certainty, though, is that wave-particle duality is a fundamental aspect of quantum physics. It tells us that the classical picture of the world, where things are either particles or waves, just doesn't apply at the quantum level. In the quantum realm, things are much stranger than we can imagine. Particles exist as waves of probability, and their behavior is influenced by observation. And as we begin to understand more about wave-particle duality, we start to realize that reality, at its core, is far stranger and more mysterious than we ever imagined. It also raises some profound philosophical questions. If reality exists as a cloud of probabilities, how can we trust what we observe? If observation itself influences the outcome, does that mean we are creating reality? Are we just passive observers, or are we active participants in the shaping of the world around us? These are deep, existential questions that quantum physics doesn't fully answer, but it certainly makes us rethink how we perceive the world. So, as we continue our exploration of the quantum universe, remember this: the strange behavior of particles is not just an oddity or a quirk. It's a window into the very fabric of reality itself. It's a reminder that the universe doesn't always follow the rules we expect, and sometimes the most basic assumptions we make about the world can turn out to be completely wrong. In the quantum world, things aren't always what they seem. And that's exactly why it's so fascinating. Let's now take a moment to explore another fascinating aspect of the quantum world: superposition. This is the idea that particles can exist in multiple states at once, not in a random, chaotic way, but in a well-defined probability cloud, like a wave of potential outcomes. Superposition challenges our most basic understanding of how things should behave in the universe. We're used to thinking of things as existing in a single state. Either a particle is in one place or it's somewhere else. But in the quantum world, that's not how it works. Imagine you have a single electron. Normally, we think of it as a particle, a tiny point that exists somewhere in space, moving around. But when it's not being observed, this electron exists in a superposition. It's not just in one place or the other. It's in all places at once, existing as a wave of probabilities. It's only when we measure the electron that it chooses a location. But before that measurement, it's spread out in a cloud of possibilities, all of which could be real. This concept is one of the cornerstones of quantum mechanics and a direct consequence of wave-particle duality. Superposition means that until a particle is observed, it doesn't have a definite state. Instead, it exists in all possible states at once. This can be difficult to wrap your head around, because our everyday experiences just don't prepare us for this kind of behavior. In the world we see, objects can only be in one state at a time. But in the quantum world, superposition tells us that the rules are different. One of the most famous examples of superposition is the double-slit experiment, which we touched on earlier. When particles like electrons are fired through two slits without being observed, they create an interference pattern on the other side, acting like waves. This suggests that, in some sense, the electrons are going through both slits at the same time. It's only when we observe them that they behave like particles, going through one slit or the other. But until then, they're in a superposition of both possibilities. The famous Schrödinger's cat thought experiment helps illustrate this idea. Imagine a cat inside a sealed box, along with a radioactive atom. The atom has a 50% chance of decaying, which would trigger the release of poison, killing the cat. If the atom hasn't decayed, the cat remains alive. In quantum mechanics, until we open the box to check, the atom is in a superposition of decayed and not decayed states, and the cat is both alive and dead at the same time. It's only when we observe the system that the wave function collapses, and the cat becomes either alive or dead. Schrödinger's thought experiment was meant to show the absurdity of applying quantum mechanics to large objects like cats, but it illustrates the bizarre nature of superposition in a way that sticks with us. Now, you might be wondering, how does this all fit together? If everything in the quantum world is in a superposition of states, then why do we see a consistent reality? Why don't we see everything as blurry, shifting, or uncertain? The answer lies in a concept called decoherence. While quantum systems like electrons can exist in superposition, once they interact with their environment, they lose their quantum coherence and collapse into a single state. Decoherence happens incredibly quickly in macroscopic systems, which is why, in our everyday world, we don't see superposition in action. It's a phenomenon that happens only at the smallest scales of reality. The way decoherence works is like this. Imagine a quantum particle, such as an electron, existing in a superposition of being in multiple places at once. But when the electron interacts with other particles, such as molecules in the air, the different possibilities start to merge together. As the system becomes more entangled with its environment, the superposition of states becomes less distinguishable, and the electron collapses into one definite state. This collapse is what we observe in the classical world. The electron is either here or there, but it's never both at once. Decoherence also helps explain why we don't see quantum weirdness in our everyday lives. If we could somehow isolate a system from its environment, we might be able to observe superposition in action on a larger scale. But in the real world, everything is constantly interacting with its environment. That's why objects in our world behave according to classical physics, not quantum mechanics. Even though everything is fundamentally quantum, the effects of superposition and wave-particle duality are so subtle at macroscopic scales that they're practically invisible to us. This doesn't mean quantum mechanics is irrelevant to the macroscopic world. Far from it. In fact, quantum principles are at the heart of some of the most important technologies we use today. Take semiconductors, for example. The transistors inside your phone or computer rely on quantum mechanics to function. Superposition and quantum tunneling are key principles that allow these devices to process information in incredibly small spaces. Quantum mechanics also underpins the science of lasers, MRI machines, and many other modern technologies. But even beyond technology, the concept of superposition raises profound questions about reality itself. If particles can exist in multiple states at once, what does that mean for the world we perceive? In a way, quantum mechanics challenges the very nature of what it means to know something. When we observe a particle, we collapse its wave function into one state. But until we observe it, it exists in all states simultaneously. This suggests that reality, at the quantum level, isn't fixed until we look at it. It's as though our perception is what gives the universe its shape. This brings us to a fascinating idea, that consciousness might play a role in shaping reality. Some interpretations of quantum mechanics suggest that the observer is an active participant in the collapse of the wave function. While this is still a topic of debate, it raises a thought-provoking question. Could consciousness itself be a part of the quantum process? Could our awareness be entangled with the fabric of reality, influencing what we observe and experience? This idea ties into a larger philosophical question about the relationship between mind and matter. For centuries, philosophers have wondered about the nature of consciousness and its role in shaping the world around us. Quantum mechanics adds an intriguing layer to this conversation, suggesting that perhaps our minds aren't separate from the universe, but deeply intertwined with it. If the universe is made up of probabilities, and our observation collapses those probabilities into reality, then perhaps we're not just passive observers of the universe, but active participants in its unfolding. Superposition also raises questions about free will. If the universe is governed by probabilities, then does that mean everything is predestined? Or do we have the power to influence the outcomes we experience? While quantum mechanics doesn't offer a direct answer to these questions, it does suggest that the universe is much more fluid and dynamic than we may have once believed. The very fabric of reality, it seems, is shaped by possibility, by chance, and by the strange, delicate dance between observation and outcome. And this brings us to one final thought. What is the nature of reality itself? If everything in the quantum world exists in superposition, where does that leave us? Is reality just a collection of probabilities, constantly shifting and changing until we observe it? Or is there something more, something deeper, beyond the veil of observation? Quantum mechanics doesn't give us all the answers, but it opens up a world of possibilities. It invites us to question the very nature of existence and to rethink what we know about the universe and our place within it. Now, let's turn our attention to the incredibly strange concept of quantum entanglement. This is one of the most mind-bending and fascinating phenomena in quantum mechanics, and it challenges our classical understanding of how the universe works. Entanglement is a kind of invisible thread that connects particles across space and time. It's a bond so deep that the state of one particle instantly influences the state of another, no matter how far apart they are. In a way, the particles are like distant twins, each mirroring the other's actions in real time, regardless of the distance between them. Entanglement was first predicted by Einstein, who famously referred to it as spooky action at a distance. He was skeptical of the idea, as it seemed to defy the laws of relativity, where nothing should be able to travel faster than the speed of light. And yet, quantum mechanics suggested something entirely different. If two particles are entangled, the state of one particle is directly tied to the state of the other, no matter how far apart they are. This connection appears to be instantaneous, which seems to break the rules of causality as we understand them. Let's explore what happens in an entangled system. Imagine two particles, say electrons, that interact with one another in such a way that their states become linked. Once they're entangled, measuring the state of one particle will immediately determine the state of the other, even if they are light years apart. So, if you measure the spin of one electron, you'll instantly know the spin of the other, regardless of whether it's sitting right next to you or on the other side of the universe. The particles aren't communicating with each other across space in the traditional sense. There's no signal traveling between them, no information being passed back and forth. The very act of measuring one particle's state seems to instantaneously determine the state of the other, as if they're somehow linked by a shared, hidden connection. Now, you might be wondering how this could be possible. If information is traveling faster than light, then how can it respect the laws of relativity? The key is that entanglement doesn't violate the no communication theorem. What happens is that when two particles become entangled, they share a quantum state. Once this state is shared, it's not that the particles are sending information to each other, but rather that their properties are inherently linked. It's not about faster-than-light communication. It's about a fundamental connection that exists between the particles at the quantum level. The experiment that demonstrated this mind-bending phenomenon came in the form of the famous Bell's theorem experiments. In the 1960s, physicist John Bell formulated a set of inequalities that could be tested to determine whether the strange predictions of quantum mechanics, like entanglement, were real. Bell's inequality was designed to show whether quantum mechanics could be reconciled with the concept of local realism, the idea that objects can only influence each other through direct interactions, and that information cannot travel faster than the speed of light. When experiments were carried out to test Bell's inequality, they found that quantum mechanics indeed predicted results that defied the limits of local realism. Entangled particles seemed to influence each other faster than light could travel, and the results suggested that the universe is far stranger than we could have ever imagined. But while the experimental evidence for entanglement is strong, there's still a lot of mystery surrounding it. For one thing, we don't understand how or why the particles are connected. We know that they are, but the mechanics of this quantum bond are still a matter of active research and speculation. Some physicists have even posited that entanglement may be a fundamental property of the universe, woven into the very fabric of reality. It might be the key to understanding the quantum structure of space-time itself. The very idea that information can be shared across vast distances instantaneously, without a signal or communication, challenges our classical notions of space, time, and causality. Entanglement is so much more than just a theoretical curiosity. It has profound implications for technology, particularly in the realm of quantum computing and quantum cryptography. Quantum computers, which use qubits instead of classical bits, rely on the power of entanglement. A quantum computer doesn't just process information one bit at a time. Instead, it can harness the power of entanglement to process many possibilities at once. This exponential parallelism means that quantum computers could one day solve problems that are beyond the reach of even the most powerful classical computers. Similarly, quantum cryptography is built on the principles of entanglement. If two parties share an entangled pair of particles, they can communicate in a way that is impossible for an eavesdropper to intercept without disrupting the system. Any attempt to measure or observe the entangled particles will collapse their state and immediately alert the communicating parties to the presence of a potential interceptor. This could one day lead to perfectly secure communications, using the strange and delicate properties of quantum mechanics to safeguard our most private information. But let's pause here and think about what entanglement really means on a deeper, more philosophical level. Entanglement challenges our assumptions about the separateness of objects in the universe. In our everyday experience, we assume that objects are distinct, separate from one another, existing independently of each other. But quantum mechanics, and especially entanglement, suggests that this separateness is an illusion. The more we study the quantum world, the more we realize that everything is connected, entangled, woven together in ways we don't fully understand. This interconnectedness doesn't just apply to particles. It might be a fundamental characteristic of the universe itself. Entanglement also brings up questions about the nature of reality. If particles can be instantaneously linked across vast distances, what does that say about the concept of space? Is space itself an illusion? Are we, as human beings, simply perceiving a very limited version of reality, one that doesn't fully capture the underlying quantum structure of the universe? The idea that entangled particles don't respect the usual rules of space and time challenges our deeply held beliefs about the nature of reality. It asks us to reconsider the boundaries of what's possible, pushing us to think beyond the classical framework that has shaped our understanding for centuries. The concept of quantum entanglement also has implications for our understanding of information. Traditionally, information is something that's stored, transmitted, and processed. But in the quantum world, information behaves differently. It's not just something that can be measured and observed. It's something that's fundamentally woven into the very fabric of reality. Information can exist in multiple states at once, and its properties can be shared between entangled particles instantaneously. This idea of information as a fundamental component of the universe is one of the most profound insights of quantum theory. It opens the door to new possibilities for understanding the relationship between the physical world and the information that governs it. At the heart of all of this is a deep, unresolved mystery. Entanglement forces us to ask questions that go beyond the realm of science and into the realm of philosophy. What does it mean to be connected? What does it mean to observe the universe? And what role does consciousness play in that observation? Can the strange, interconnected world of quantum mechanics help us understand the mind and the nature of awareness itself? These questions may not have answers yet, but they are worth pondering as we delve deeper into the quantum world. Now, let's take a moment to dive into a phenomenon that's not just strange, it's outright mind-boggling: quantum tunneling. This is a process that, on the surface, seems to defy logic itself. Imagine a particle, like an electron, traveling toward a barrier that, according to classical physics, it should never be able to pass through. The barrier is simply too high or too thick, and the particle doesn't have enough energy to jump over it. Classical mechanics would predict that the particle would just bounce back, unable to penetrate the wall, but quantum mechanics is more forgiving, or perhaps more bewildering. Quantum tunneling says, no, that particle has a chance. In fact, it's not just a chance, it's a genuine possibility. The particle doesn't need to climb over the barrier. Instead, it can pass through the wall as if the wall itself isn't really there. The particle tunnels through the barrier, appearing on the other side, even though classical physics insists it should be impossible. This may sound like pure science fiction, but it's a phenomenon that has been observed countless times, from the behavior of subatomic particles in particle accelerators to the operation of everyday devices like tunnel diodes, and even in processes that sustain life itself. So, how does quantum tunneling work? To understand this, we need to delve a little into the wave-particle duality that we've touched on earlier. In quantum mechanics, particles like electrons are not just points with a definite position. They are also waves of probability. These waves spread out over a range of possibilities, and the particle doesn't occupy a single, well-defined position until it's measured. Instead, its position is a probability cloud, where certain locations are more likely than others. Now, when this probability wave encounters a barrier, it doesn't just stop dead at the edge like a ball hitting a wall. No, the the wave spreads out and starts to leak through the barrier. In some cases, the wave will extend all the way through the barrier and beyond it. This means that there's a probability, however small, that the particle can be found on the other side of the barrier, even though classical physics would say it should be impossible. The particle effectively tunnels through the wall, and it's as though it never encountered any resistance at all. But this doesn't mean that every particle always tunnels through every barrier. The probability of tunneling depends on several factors: the size of the barrier, the energy of the particle, and the distance the particle has to travel. The thicker the barrier and the less energy the particle has, the less likely it is to tunnel through. However, the important point is that tunneling is not just a possibility. It's a very real, observable effect, and it has profound implications for the way we understand the universe. Quantum tunneling plays a crucial role in several natural and technological processes. Take, for example, the Sun's nuclear fusion. In the core of the Sun, hydrogen atoms are fused together to form helium, releasing an enormous amount of energy in the process. According to classical physics, these hydrogen nuclei should repel each other due to their positive charge. They should never have enough energy to overcome this repulsion and fuse together. But quantum mechanics comes to the rescue. Thanks to quantum tunneling, the particles can pass through the energy barrier that keeps them apart, allowing the fusion reactions to happen. Without tunneling, the sun would never shine. In the world of technology, tunneling is also at the heart of some of the most important devices. For instance, the tunnel diode, a type of semiconductor, relies on tunneling to function. This device is faster and more efficient than regular diodes because it takes advantage of the quantum effects that allow particles to pass through barriers that would otherwise block them. Quantum tunneling also plays a role in scanning tunneling microscopes, which are used to image surfaces at the atomic level. These microscopes work by measuring the tunneling current that flows between a sharp tip and the surface being examined, revealing the structure of the surface with incredible precision. But beyond its practical applications, quantum tunneling also forces us to rethink our understanding of time, space, and causality. In the classical world, when an object encounters an obstacle, it either goes around it or over it, but it never just disappears and reappears on the other side. Quantum mechanics, on the other hand, tells us that particles can, in a sense, break the rules and take shortcuts. They can bypass obstacles that they shouldn't be able to overcome. This idea challenges our conventional understanding of how reality works. How can something pass through a solid wall without breaking the laws of physics? The answer lies in the probabilistic nature of the quantum world. Particles don't always follow the paths we expect. Instead, they can explore all possible outcomes, and sometimes that means finding their way through seemingly impossible barriers. This leads us to a deeper philosophical question. If particles can do the impossible, what does that say about the limits of our own reality? Quantum tunneling suggests that the universe is far more flexible than we've been taught. It operates on principles that seem illogical and unpredictable, yet they are perfectly consistent and measurable. The more we study quantum mechanics, the more we realize that our intuitive, everyday understanding of reality is a very limited perspective. The true nature of the universe may be far stranger, more fluid, and more open to possibilities than we've ever imagined. Quantum tunneling also raises interesting questions about the nature of time. If a particle can tunnel through time and space, does this imply that time itself might not be as fixed as we think? Could there be ways to manipulate time on a quantum level, or even travel through time itself? While we're far from having any practical answers to these questions, the very possibility of time manipulation in the quantum world adds another layer of intrigue to the study of quantum physics. Ultimately, quantum tunneling invites us to think about the world in new and radical ways. It challenges our understanding of how the universe behaves at the smallest scales, and it forces us to confront the possibility that reality is far more malleable than we've been led to believe. As we continue to unravel the mysteries of quantum mechanics, tunneling will undoubtedly play a key role in shaping our understanding of the universe and its fundamental laws. But for now, all we can do is marvel at the strange beauty of quantum tunneling and wonder what other surprises the quantum world has in store for us. Now, let's venture into another layer of quantum mechanics that brings us closer to understanding the very nature of reality: quantum entanglement. This is one of the most bizarre, yet experimentally confirmed, phenomena in the quantum realm. In a sense, entanglement is the quantum world's ultimate magic trick. It's like a cosmic connection, where two particles, no matter how far apart they are, remain mysteriously linked. No matter the distance between them, no matter if they're on opposite ends of the universe, what happens to one particle will instantaneously affect the other. And yes, I mean instantaneously, faster than the speed of light. If this sounds impossible, that's because, in the classical world, it is. But in the quantum world, it's perfectly real. To understand entanglement, let's take a step back. Imagine you have two particles, say two electrons. These electrons are created in such a way that their properties are linked in a special, quantum fashion. One electron might have an up spin, while the other has a down spin. But here's where it gets strange. Until you measure these particles, their spins are not actually decided. Instead, they exist in a superposition, a mix of up and down at the same time. This is quantum weirdness at its finest. Both outcomes exist in probability until they are observed. Now, when you measure one particle, say electron A, and find that it has an up spin, something immediately happens to electron B. In an instant, electron B's spin becomes down, even if it's light years away. The measurement of one particle instantly determines the state of the other, regardless of the distance between them. This kind of connection between particles is called quantum entanglement. The particles are linked in such a deep way that the state of one particle can never be described independently of the other, even if they are far apart in space. The truly mind-boggling part is that this instant communication between particles happens faster than the speed of light. It doesn't just violate the principles of classical physics. It directly defies the understanding of space and time itself as we know them. Einstein famously called this phenomenon spooky action at a distance, because it seemed to suggest that information could travel faster than light, something that no classical theory of physics allows. But quantum mechanics doesn't play by the same rules. In fact, it doesn't play by any rules that we're used to in the macroscopic world. You might be wondering, how is this possible? How can two particles be so deeply connected that a change in one affects the other instantly, even across vast distances? The answer lies in the nature of quantum information. Entanglement is a form of quantum correlation. When two particles are entangled, their quantum states are deeply linked in such a way that the state of one particle can't be described without referencing the state of the other, no matter how far apart they are. They are part of a single quantum system, even if they're separated by light years. But this doesn't mean that information is traveling faster than light. The act of measurement doesn't transmit any usable information between the particles. It's not like one particle is sending a signal to the other. Instead, both particles exist as a single system, and the measurement of one simply forces the entire system to choose a state. It's as though the universe, once you look at one particle, decides that the other particle must instantly align with it. Entanglement has been confirmed in countless experiments. One of the most famous experiments was conducted by physicists Alain Aspect, who in the 1980s showed that entangled particles could communicate faster than the speed of light, violating what was once thought to be an absolute law of nature. Aspect's work and similar experiments have verified that entanglement is not just a quirky theory, but an actual, observable phenomenon in the quantum world. So, what does this all mean for us? Well, beyond the mind-bending implications for our understanding of space, time, and causality, quantum entanglement holds promise for some incredibly exciting technologies. One of the most talked about applications is quantum computing. Quantum computers will rely on entanglement to process information in ways that traditional computers cannot. In classical computing, each bit of information is in one of two possible states, 0 or 1. But in quantum computing, each qubit, the quantum equivalent of a bit, can exist in multiple states simultaneously, thanks to superposition. And when qubits become entangled, they can perform complex computations much more efficiently than classical bits. In other words, entanglement could enable quantum computers to solve problems that would take classical computers millennia to solve, like factoring large numbers or simulating complex molecular interactions. Another fascinating application of entanglement is in the field of quantum cryptography. Because entangled particles are linked in such a way that the measurement of one immediately determines the state of the other, any attempt to eavesdrop on a quantum communication channel will immediately be detectable. If someone tries to intercept the transmission of quantum information, the very act of measuring the entangled particles will disrupt their state, alerting the sender and receiver that something is wrong. This makes quantum encryption incredibly secure and practically immune to hacking, an exciting prospect in an age where cybersecurity is a major concern. But entanglement doesn't just apply to particles and computers. It challenges the very nature of reality and our understanding of how information flows in the universe. If entanglement is real, then the universe is much more interconnected than we've ever imagined. It suggests that everything is, in a sense, linked together in a vast quantum web, where the state of one particle can influence the state of another, no matter how far apart they are. This web of quantum connections might hold the key to understanding the true nature of reality itself. One of the biggest philosophical questions raised by quantum entanglement is the issue of locality, the idea that objects are only influenced by their immediate surroundings. In classical physics, locality is a given. Objects interact only with their immediate environment. But quantum entanglement challenges this principle. It suggests that particles can be connected across vast distances, violating the idea of a local reality. If entanglement is real, then information in the universe doesn't have to travel through space as we understand it. Instead, it can be instantaneously shared between distant particles, suggesting that the universe itself may not be as separate and disconnected as it seems. Instead, everything may be part of one giant, interconnected quantum system. Quantum entanglement is a strange, unsettling concept that forces us to rethink everything we know about the universe. It's a phenomenon that defies our classical intuitions about space, time, and cause and effect, and it has the potential to revolutionize technology in ways we're only beginning to understand. And perhaps more than any other concept in quantum mechanics, entanglement highlights the vast strangeness of the quantum world, a world where particles are connected across time and space, where reality is not as fixed as we think, and where the very fabric of the universe is far more mysterious than we can fully comprehend. Let's continue this journey into the quantum realm and explore one of the most fascinating and perplexing concepts in all of physics, quantum superposition. This concept is not just central to understanding quantum mechanics, but it also leads us into the world of the bizarre, where particles exist in multiple states at once, and where the line between the possible and the real becomes wonderfully blurred. Superposition is the idea that a quantum system, like a particle, doesn't have a single definite state until we observe it. Instead, it exists in a superposition, a combination of all possible states, until a measurement forces it to choose one. Think of it like this. Imagine you have a coin. You flip it, and the coin could land heads or tails. In classical physics, you would assume that at any given point, the coin is in one of those two possible states. But in the quantum world, things are different. Before you observe it, the coin is in a superposition of both heads and tails at the same time. It's not that the coin is half heads and half tails, it's that it exists in a state where it is both heads and tails simultaneously. Only when you observe it does it collapse into one of those states. This idea may sound completely counterintuitive, and that's because it is. Our everyday experience teaches us that things exist in definite states, that objects have properties we can measure, and that reality behaves in predictable ways. But quantum mechanics doesn't play by these rules. Instead, it suggests that at the most fundamental level, things don't exist in a fixed state until they're measured. They exist in a cloud of probabilities, where all possible outcomes are mixed together until the act of observation forces a single, definite outcome. Let's dive a little deeper into this with an example that really illustrates the strange nature of superposition, one that's often called Schrödinger's cat. This famous thought experiment, proposed by physicist Erwin Schrödinger in 1935, is a way of showing how superposition works on a larger scale. In the experiment, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the Geiger counter detects radiation from the decaying atom, the poison is released, killing the cat. If the atom doesn't decay, the cat remains alive. Now, according to quantum mechanics, the radioactive atom exists in a superposition of decayed and not decayed states, which means that, by extension, the cat is both alive and dead at the same time. The cat is in a superposition of both possibilities until someone opens the box to observe it. At that moment, the wave function collapses, and the cat is either alive or dead, depending on the state of the atom. The key point here is that the cat's fate is tied to the atom's behavior, and both the cat and the atom exist in a superposition of states until the measurement takes place. Schrödinger's cat wasn't meant to be taken literally. It was a way for him to point out the strange and seemingly absurd implications of quantum mechanics when applied to the macroscopic world. But it underscores a crucial point. Quantum systems don't behave like the objects we encounter in our daily lives. They exist in multiple states at once, and only through observation do they choose one. This doesn't mean the cat is literally alive and dead at the same time in any classical sense. Instead, it means that, at the quantum level, particles don't have definite states until we measure them. Until then, they exist in a blend of all possible outcomes. This idea of superposition doesn't just apply to particles like electrons. It's a feature of all quantum systems. And as strange as it sounds, superposition is not just a theoretical idea. It has been experimentally verified in countless experiments. One of the most famous of these is the double-slit experiment. In this experiment, particles like photons or electrons are fired at a wall with two slits. If you don't observe which slit the particle goes through, it behaves like a wave, creating an interference pattern on the screen behind the slits. This pattern shows that the particle has passed through both slits at the same time, interfering with itself. It's in a superposition of both paths until it's measured. But here's the twist. If you set up a detector to observe which slit the particle goes through, the interference pattern disappears. The particle acts as though it only passed through one slit, like a tiny ball that went through a single opening. This is the weirdness of quantum mechanics. When you observe the system, it behaves as a particle, with a definite position. But when you don't observe it, it behaves like a wave, existing in a superposition of all possible states. The key takeaway here is that quantum systems don't have a definite state until they're measured. Before measurement, particles exist in a superposition of all possible states, and the act of measurement collapses that superposition into one definite state. This is the heart of quantum mechanics, and it challenges our fundamental assumptions about reality. In the classical world, things exist in a definite state, independent of whether we observe them. But in the quantum world, observation is what forces the system to choose a state, and before that, all possibilities are in play. Superposition is not just an abstract idea or a quirk of quantum mechanics. It's a key feature that makes quantum computing so powerful. In classical computing, a bit can either be a 0 or a 1. But in quantum computing, a qubit can exist in a superposition of both 0 and 1 at the same time. This allows quantum computers to process vast amounts of information in parallel, exploring multiple solutions to a problem simultaneously. It's like having a million computers running at once, but in the space of a single qubit. This parallelism is what makes quantum computers so powerful, and it's all possible because of superposition. Superposition is also the reason why quantum mechanics can seem so strange and counterintuitive. We live in a world where things have definite properties, where objects exist in specific locations, and where outcomes are predictable. But at the quantum level, these assumptions break down. Particles don't have definite properties until they're measured. They don't follow a single, predictable path. Instead, they exist in a cloud of possibilities, and the act of observation brings one of those possibilities into reality. This doesn't mean that reality is arbitrary or random. It just means that our classical understanding of the world doesn't apply at the quantum level. The quantum world is governed by its own set of rules, and superposition is one of the key features of those rules. At its core, quantum superposition is a reminder that the universe is far stranger and more complex than we can even imagine. It challenges our intuitions about space, time, and reality, and it forces us to rethink the nature of existence itself. In the quantum world, everything is in flux, existing in multiple states at once, until we observe it and force it to take a definite form. It's a world of infinite possibilities, a world where the act of observation shapes reality, and where the future is not set until we look at it. So, the next time you encounter something that doesn't quite make sense in the quantum world, when particles behave in ways that defy your intuition, remember that it's just another layer of reality being revealed. And when we peel back that layer, we find that the universe is even more strange and beautiful than we could have imagined. Let's take a moment to explore one of the most mysterious and elusive concepts in quantum physics: entanglement. If there's one idea that truly captures the weirdness of the quantum world, it's entanglement. It's one of the most puzzling phenomena in all of science, and yet, it's been experimentally verified over and over again. Entanglement describes a connection between two or more particles in which their properties are linked, no matter how far apart they are. When particles are entangled, the state of one particle is directly tied to the state of another, even if they are light years apart. It's as if these particles are mysteriously communicating with each other, instantaneously, faster than the speed of light, defying all the usual rules of space and time. This idea of entanglement was first proposed by Albert Einstein in 1935. He famously referred to it as spooky action at a distance. He couldn't quite accept that two particles, separated by vast distances, could influence each other instantaneously. According to Einstein's view of the world, nothing could travel faster than light, and there was no way particles could communicate faster than that. But quantum mechanics, as it turns out, doesn't care much for these classical ideas. It operates in a fundamentally different way. In quantum mechanics, when two particles become entangled, their individual states are no longer independent. Instead, they share a joint state. If you measure one particle, you instantly know the state of the other, no matter how far apart they are. This isn't just a matter of the particles being correlated. It's as though they are part of a single, unified system. And the strangest part? The entangled particles can be far apart, separated by vast distances in space, yet a measurement of one will instantaneously affect the state of the other. Let's break this down a bit with a thought experiment. Imagine you have two particles, A and B, that are entangled. They are in a superposition of states. Neither one has a definite property until measured. For example, let's say you're measuring their spin, which can either be up or down. Before measuring, both particles are in a superposition of both spin up and spin down. But as soon as you measure particle A and find it has spin up, particle B's state will instantly collapse into spin down, even if particle B is light years away. It's as though particle A's measurement instantly decides the state of particle B, no matter how far apart they are. This isn't some theoretical quirk. It has been tested in real experiments. In 1964, physicist John Bell formulated what became known as Bell's theorem. Bell's work showed that if quantum mechanics were correct, then entangled particles must exhibit correlations that couldn't be explained by any local hidden variables, meaning they couldn't have been influenced by factors outside of their entangled state. In other words, quantum entanglement violates the classical notion of locality, the idea that objects are only influenced by their immediate surroundings. And in 1982, physicist Alain Aspect and his team conducted an experiment that tested Bell's theorem. The results confirmed that quantum mechanics predictions about entanglement were true. When particles are entangled, their properties are deeply connected, even when separated by vast distances. But how does this work? How can particles be entangled and influence each other instantaneously, faster than the speed of light? The truth is, we don't really know. Quantum mechanics doesn't offer a clear explanation for how this instantaneous connection happens. But the experimental evidence is undeniable. And it's one of the reasons quantum mechanics is so mind-bending, because it forces us to question our most basic assumptions about space, time, and reality. The phenomenon of entanglement has many fascinating implications, and it's one of the key principles behind the emerging field of quantum computing. In a quantum computer, qubits, the quantum equivalent of classical bits, can be entangled with each other, allowing quantum computers to perform complex calculations in parallel. The entanglement of qubits is what makes quantum computing so powerful. It enables them to process vast amounts of data simultaneously, exploring many possibilities at once. But entanglement isn't just a theoretical curiosity or a tool for computing. It's a window into the very nature of reality. Entanglement challenges our classical view of the world. In the classical world, we think of objects as separate and independent, each with its own properties. If you measure one object, it doesn't affect the state of another unless there's some force acting on both. But in the quantum world, things are different. When particles become entangled, they are no longer separate. They form a unified system, and the measurement of one particle affects the other instantaneously. This challenges our understanding of locality and causality, the idea that events are connected by time and space. It also forces us to reconsider the nature of information. In classical physics, information is transmitted through physical channels, signals that travel through space and time. But in the quantum world, entanglement suggests that information can be shared instantaneously, without any need for physical transmission. This has led to the development of quantum communication technologies, which rely on the principles of entanglement to transmit information securely. Quantum key distribution, QKD, is one such technology that uses the principles of quantum mechanics to create unbreakable encryption, ensuring that any attempt to eavesdrop on the communication will be detected. Entanglement has even led some physicists to propose radical new ideas about the structure of reality itself. One idea is that the universe is fundamentally interconnected, that everything is entangled in some deep and profound way. This idea is known as quantum non-locality. It suggests that the boundaries between objects and events are not as fixed as we think, that everything in the universe might be connected in ways we can't yet comprehend. This is a fascinating idea, but it's still very much a subject of debate among physicists. Some believe that the strange correlations seen in entanglement experiments are just a result of the mathematical structure of quantum mechanics, while others think they point to a deeper, more profound connection between all things. So, what does this all mean for our understanding of reality? Well, it means that the quantum world doesn't play by the same rules as the classical world. It's a world where particles can be in multiple states at once, where they can be connected across vast distances, and where the very act of observation shapes the outcome. It's a world where uncertainty, probability, and interconnectedness are the rule, not the exception. Entanglement also raises profound philosophical questions about the nature of reality. If two particles can be entangled and affect each other instantaneously, does that mean they are part of a single, unified system? And if everything in the universe is ultimately entangled, what does that say about our place in the cosmos? Are we all connected in ways that go beyond our understanding? One thing is certain. Quantum entanglement is one of the most fascinating and mysterious aspects of quantum mechanics. It shows us that the universe is far stranger than we could have ever imagined. It's a world where particles are not independent, where they can be linked across vast distances, and where the act of measurement plays a crucial role in shaping reality. As we continue to explore the strange and wonderful world of quantum physics, we may find that entanglement is just the beginning. There may be even deeper mysteries waiting to be uncovered, mysteries that could reshape our understanding of the universe itself. Now, let's venture deeper into the heart of quantum mechanics and explore the phenomenon of wave-particle duality. It's a concept that stretches our intuitions to the breaking point. The idea that particles, such as light and electrons, can act both as particles and waves is one of the most perplexing aspects of quantum mechanics. It's a contradiction that doesn't make sense in the classical world. After all, when you think of a particle, you imagine something small and discrete, like a tiny billiard ball, with a definite position and velocity. But when you think of a wave, you imagine something smooth, spread out, and capable of interference. And yet, quantum mechanics tells us that at the smallest scales, particles can behave as both. It all began with the discovery that light, long thought to be a continuous wave, also behaves like a particle in some situations. This was first proposed by Albert Einstein in 1905, when he suggested that light could be thought of as discrete packets of energy, which he called quanta or photons. This explanation was pivotal in explaining the photoelectric effect, where light shining on a metal surface can cause the emission of electrons. Einstein's idea was revolutionary because it suggested that light, which had been thought of as a pure wave, could also act as a particle. But just as scientists were coming to terms with the idea that light could behave as both a particle and a wave, a new set of experiments introduced an even stranger idea. In the early 20th century, the famous double-slit experiment was adapted to test the behavior of particles. If you fire a stream of electrons, tiny particles, through two slits in a barrier, you'd expect to see a pattern on a screen behind the slits that reflects the discrete nature of the electrons, much like the pattern you get from shooting balls through two holes. But what happens in the quantum world is far stranger. Instead of showing a simple two-peak pattern, the electrons create an interference pattern, much like waves of water passing through slits and interfering with each other. This experiment raised a puzzling question. How could individual particles create a pattern that's characteristic of waves? If you treat the electron like a particle, it should pass through one slit or the other, and you'd expect two peaks on the screen, corresponding to the two slits. But instead, what you get is a pattern of light and dark bands, an interference pattern, suggesting that the electron is somehow behaving like a wave, passing through both slits at once and interfering with itself. Even more perplexing, when you try to measure which slit the electron goes through, the interference pattern disappears, and the electron behaves like a particle again. This suggests that the mere act of observation has an effect on the behavior of the electron. This is the crux of wave-particle duality. A particle can behave like both a particle and a wave, depending on how you observe it. The truth is, quantum mechanics doesn't allow us to think of particles as simple, discrete objects anymore. Instead, it describes particles as having a dual nature, both wave-like and particle-like. When particles such as electrons are unobserved, they exist in a superposition of states, meaning they can simultaneously be in multiple places or states at once, much like a wave that spreads out across space. But the moment we measure or observe them, they collapse into a definite state, like a particle with a specific location. This duality isn't just limited to light and electrons. In fact, it extends to all quantum objects, even large molecules. In 1999, scientists performed an experiment using a molecule called a buckyball, a molecule made of 60 carbon atoms, and found that it, too, exhibited wave-particle duality. This was a huge discovery, as it showed that even relatively large, complex molecules could behave like quantum objects, and not just microscopic particles like photons and electrons. It seemed that wave-particle duality was a fundamental feature of the universe. But the question remains, how can something be both a wave and a particle? How can the same object exhibit two such contradictory behaviors? To understand this, we need to let go of our classical understanding of what particles and waves are. In the quantum world, particles don't have well-defined positions and velocities until they are measured. Instead, they exist as a wave function, a mathematical description of all the possible positions and states a particle could occupy. The wave function spreads out across space, describing a range of possibilities, and when you observe the particle, the wave function collapses, and the particle takes on a definite state. But this is still just a mathematical description. The wave function is not a tangible thing that you can touch or see. It's simply a tool we use to calculate the probabilities of where a particle might be or what state it might be in. The wave function doesn't tell us what the particle is doing when it's not being observed. It only gives us the likelihoods of various outcomes. This is where things get even stranger. In the quantum world, the particle doesn't have a definite state until it is observed, and the act of observation determines the outcome. In a sense, the very act of measurement creates the reality we experience. So, if a quantum object is both a particle and a wave, how do we reconcile these two descriptions? The answer lies in the fact that quantum mechanics doesn't require us to choose between the two. Instead, it allows both descriptions to coexist. A particle can have properties of both a particle and a wave, depending on the context in which it is measured. It's a paradox, yes, but it's a paradox that has been experimentally verified time and time again. Wave-particle duality challenges our classical intuitions about the world. In the classical world, objects are either particles or waves, but quantum mechanics shows us that the boundary between these two concepts is not so clear. It suggests that the universe at its core is neither entirely particle-like nor entirely wave-like, but is something else entirely, a blend of both. In the quantum realm, particles don't behave like classical objects at all. Instead, they exist in a state of uncertainty, where their properties are not fixed until they are observed. This is what makes quantum mechanics so strange and difficult to grasp. It defies our everyday understanding of how the world works. But wave-particle duality isn't just a strange curiosity. It has real-world implications. It's the foundation of technologies like lasers and transistors, and it's essential to understanding the behavior of everything from atoms to molecules. In fact, many of the most important discoveries in quantum mechanics, from the structure of the atom to the development of quantum computers, rely on the principles of wave-particle duality. In quantum computing, for example, the concept of superposition, the idea that particles can exist in multiple states at once, is a direct consequence of wave-particle duality. A quantum computer uses qubits, which can be in a superposition of states, allowing them to perform multiple calculations at once. This gives quantum computers the potential to solve problems that are impossible for classical computers to handle. Without wave-particle duality, the entire field of quantum computing wouldn't be possible. Wave-particle duality also has profound philosophical implications. It challenges our understanding of reality itself. If particles can exist in multiple states at once, what does this say about the nature of the universe? Is reality fundamentally indeterminate, existing only as a set of probabilities until we observe it? And if so, what does that say about our role in shaping reality? The concept of wave-particle duality also raises questions about the nature of measurement and observation. In classical physics, Measurement is a passive process. You simply observe a system without affecting it. But in the quantum world, measurement actively influences the system, causing it to collapse into a definite state. This suggests that the act of observation plays a fundamental role in shaping the universe. It's a deeply unsettling thought. Are we truly passive observers of reality, or are we active participants in its creation? At the end of the day, wave-particle duality is just one of the many strange and beautiful features of quantum mechanics. It reminds us that the universe is not as simple as it seems. It challenges our intuitions, forces us to rethink the nature of reality, and invites us to embrace the mystery at the heart of the quantum world. And maybe that's the point. In a universe where particles are both waves and particles, and where the act of observation shapes reality, the most important lesson might be to accept the beauty of uncertainty, to let go of our need for rigid certainty, and to embrace the mystery of the quantum world. We've journeyed through the peculiarities of quantum mechanics, and now we arrive at a topic that stands at the intersection of both mystery and discovery: quantum entanglement. It's a concept so bizarre that Albert Einstein himself famously called it spooky action at a distance. To understand entanglement, we need to stretch our imaginations a little further and embrace something deeply counterintuitive. Entanglement is a phenomenon where two particles become linked in such a way that the state of one particle directly influences the state of another, no matter how far apart they are. It's as though they share a connection that transcends space and time. Entanglement was first predicted by the mathematician Erwin Schrödinger in 1935. He coined the term entanglement, or Verschränkung in German, to describe a situation where two particles, after interacting, become intertwined in a way that their properties can no longer be described independently. When two particles are entangled, their quantum states are correlated. If you measure one particle, you immediately know the state of the other, regardless of the distance between them. This is where things get spooky. It doesn't matter if the particles are on opposite sides of the universe. When one is measured, the other's state is instantly determined. It's as if information is transmitted faster than light, defying the principles of relativity that tell us nothing can travel faster than light. Einstein's discomfort with entanglement wasn't because he doubted the math, but because it seemed to imply a deeper connection between particles that didn't make sense in the classical, local view of reality. For Einstein, the idea that particles could instantaneously affect each other over vast distances was a challenge to the very fabric of causality and locality. But despite Einstein's reservations, quantum mechanics doesn't make exceptions. It insists that entanglement is a real, measurable phenomenon. And since the 1960s, numerous experiments have confirmed the existence of quantum entanglement, making it a cornerstone of quantum physics. But what does this mean for our understanding of reality? To grasp the true weirdness of entanglement, let's break it down. Imagine you have two electrons that interact with each other. After they interact, they become entangled. If you now separate these two electrons by vast distances, say one is on Earth and the other is on a distant star, an observation made on the electron on Earth will immediately reveal the state of the electron on the star, even though no physical signal can travel that fast. The particles are now forever connected, regardless of the distance between them. This isn't just a theoretical oddity. It's been demonstrated experimentally. In 1997, physicists Alain Aspect and his team conducted an experiment that confirmed the existence of entanglement. They showed that two particles, when entangled, could be measured to have correlated properties, even when separated by large distances. This experiment solidified entanglement as a real and observable phenomenon, not just a quirky feature of quantum theory. Now, let's dive into the implications of entanglement for our understanding of reality. On the one hand, entanglement challenges our classical intuitions about the separateness of objects. In classical physics, objects are distinct and localized. Each particle has its own properties that don't affect others unless they interact through known forces like gravity or electromagnetism. But in the quantum world, this view breaks down. The quantum world is deeply interconnected. Particles can share properties, influence each other, and even be entangled, regardless of the distance between them. This suggests that the boundaries of space and time are not as absolute as we once thought. In some sense, entanglement suggests that the universe might be more unified than we imagined. Perhaps, at a deeper level, everything is connected in ways we can't yet fully comprehend. But this raises another question. If particles can be instantaneously connected across vast distances, what does this mean for the idea of information? Does entanglement imply that information can travel faster than the speed of light? The answer is surprisingly subtle. While entanglement links particles in a way that seems instantaneous, it doesn't actually allow for faster-than-light communication. This is because entanglement doesn't transmit any usable information by itself. If you measure one particle, you instantly know the state of the other, but you cannot control the outcome of the measurement. The result is random, and you can't use this randomness to send a message. Therefore, even though entanglement seems to defy space and time, it doesn't violate the speed of light limit on information transfer. Entanglement also leads to what's called the EPR paradox, named after Einstein, Podolsky, and Rosen, who first pointed out the strange implications of quantum mechanics in 1935. They argued that if quantum mechanics were complete, it would mean that particles could instantaneously influence each other over vast distances. This seemed to imply that there was some hidden, non-local reality that quantum mechanics was not describing. Einstein and his colleagues were uncomfortable with this idea, but as we've seen, experiments have since shown that entanglement is indeed real and not something we can dismiss. At this point, we might be tempted to ask, what does all of this mean for the nature of reality? If quantum particles are entangled, what does this say about the structure of space and time? It's hard to say definitively, but entanglement suggests that the universe might not be as separate and isolated as we think. In some sense, everything could be connected at a deeper level. Some physicists have even speculated that entanglement could be the key to understanding the fabric of space-time itself. Perhaps, they argue, space-time is not a fixed, unchanging backdrop, but a dynamic, interconnected web that is shaped by the entanglements between particles. This idea is still highly speculative, but it offers an exciting new perspective on the nature of reality. In the realm of technology, entanglement has far-reaching applications, especially in the emerging field of quantum computing. Quantum computers leverage the power of entanglement to perform calculations that would be impossible for classical computers. In a classical computer, information is processed using bits, which can be either 0 or 1. But in a quantum computer, information is processed using qubits, which can be both 0 and 1 simultaneously, thanks to superposition. When qubits become entangled, they can perform computations in parallel, exploring many possibilities at once. This makes quantum computers incredibly powerful for tasks such as factoring large numbers, simulating molecular interactions, and solving optimization problems. The ability to harness entanglement for computation is one of the reasons quantum computing holds such promise for the future. Entanglement also has profound implications for cryptography. Quantum entanglement can be used to create ultra-secure communication systems. The concept of quantum key distribution, QKD, relies on the principles of entanglement to ensure that any eavesdropping on a communication will be immediately detected. If an eavesdropper tries to intercept the entangled particles, they will disturb the quantum state, alerting the sender and receiver to the breach. This makes quantum cryptography potentially unbreakable, offering a new level of security for sensitive data transmission. Despite all the exciting possibilities, quantum entanglement still leaves us with more questions than answers. While we can observe the effects of entanglement in the laboratory, understanding the deeper implications of this phenomenon is still a work in progress. What does entanglement tell us about the structure of space and time? How does it relate to the nature of consciousness and observation? And could entanglement be the key to unlocking the mysteries of the universe? One thing is certain: entanglement is a central piece of the quantum puzzle. It challenges our intuitions, defies our understanding of space and time, and invites us to think in new, more interconnected ways. It's a reminder that the universe is stranger, more mysterious, and more beautiful than we can imagine. And perhaps, as we continue to explore the depths of quantum mechanics, we'll uncover even more surprises about the nature of reality, the interconnection of all things, and the role we play as conscious observers in this grand, unfolding story. As we close this exploration of the quantum world, let's reflect on one of the most fascinating and perplexing aspects of quantum physics: the observer effect. In some ways, it's the perfect summary of what we've learned so far. In the quantum realm, the very act of observation shapes reality itself. It's as if the universe doesn't fully decide on its state until we decide to look at it. This idea isn't just a philosophical musing. It's a cornerstone of quantum mechanics, and it has real, measurable consequences. The observer effect can be traced back to the double-slit experiment. We've already discussed how particles, like electrons or photons, behave as waves when unobserved. But when we measure which slit the particle passes through, it suddenly behaves like a particle, not a wave, and the interference pattern disappears. This shift from wave-like behavior to particle-like behavior seems to be triggered by the observation itself. But why? What is it about observation that causes this transformation? And what does this say about the relationship between consciousness and reality? Physicists have spent decades grappling with this question. One possible explanation is that the act of measurement collapses the wave function. The wave function is a mathematical description of all the possible states a quantum system could be in. Before measurement, a particle exists in a superposition of all these possibilities, as though it's in multiple places at once. But when we measure it, the wave function collapses, and the particle chooses one specific state. This collapse doesn't happen unless we observe it. It's as if reality itself is suspended in a state of potential until we choose to look at it. This is known as the measurement problem in quantum mechanics. At its core, the observer effect raises profound questions about the nature of reality. If the act of observation is necessary to collapse the wave function, does this mean that consciousness plays a role in shaping the world around us? Are we, as conscious beings, co-creators of the reality we experience? This idea, which has fascinated physicists and philosophers alike, challenges our classical understanding of the universe as something that exists independently of us. It suggests that, in some sense, the universe is not a static backdrop to our lives, but an interactive, evolving system in which we play an active role. There's another layer to the observer effect that makes it even more intriguing. The observer doesn't necessarily need to be human consciousness. In many experiments, it's been shown that the act of measurement, performed by an apparatus or even another particle, causes the wave function to collapse. This leads some scientists to wonder: is it the act of measurement itself that collapses the wave function, or is it the information that becomes available to the system when we observe it? In other words, does reality depend on the availability of information, and the process of observation simply makes this information accessible to the system? One of the most mind-bending consequences of the observer effect is the idea that the future could influence the past. This may sound like science fiction, but experiments have suggested that measurements made in the present can influence past events. The delayed choice quantum eraser experiment, for example, demonstrates that a photon's behavior can be influenced by a future decision about whether or not to observe its path. The photon seems to know whether or not it will be observed, and it behaves accordingly. It's as though the particle is responding to the future before it's even been decided. This phenomenon doesn't violate the law of causality, but it does stretch our understanding of time and cause and effect. In the quantum world, the relationship between time, causality, and observation is far more flexible than we might expect. It's as though the quantum world exists in a kind of suspended animation, waiting for us to make a decision about what's real, and only then does it crystallize into the familiar reality we experience. In this way, quantum mechanics seems to suggest that the very fabric of time and space is not as fixed as we once thought. But if this is true, then where does this leave us? If the future can affect the past, what does this say about free will? Are we truly agents in our own lives, or are we simply observing a reality that's already been decided? These are some of the most profound questions raised by quantum mechanics, and though we don't yet have answers, they point to a deeper mystery at the heart of the universe. What we do know is that the observer effect suggests a much more fluid, interconnected view of reality than we've ever imagined. It hints at a universe that's not just a collection of objects and events, but a dynamic, participatory system in which we, as conscious observers, play an integral role in shaping what's real. This idea also opens up the possibility that the universe is more interconnected than we've ever realized. If the future can influence the past, it's as if time itself is not a simple, one-way progression from cause to effect, but a complex, interwoven fabric where the present, past, and future exist in a kind of quantum dance. This challenges our traditional linear understanding of time and suggests that reality may be more malleable than we think. It's as if we're living in a world where the boundaries between past, present, and future are not as solid as we once believed, and where observation is the key to unlocking the potential of this fluid, dynamic reality. The observer effect also has profound implications for the nature of consciousness itself. If consciousness can influence the outcome of quantum measurements, does this mean that consciousness is a fundamental part of the fabric of reality? Is the mind not just a passive observer of the world, but an active participant in the creation of the universe? Some physicists have suggested that consciousness plays a role in the collapse of the wave function, and that the act of observing a quantum system may be linked to the act of conscious awareness. If this is true, it would suggest that consciousness is not something separate from the universe, but something that is deeply entwined with it, shaping and creating reality at the quantum level. In this sense, quantum mechanics invites us to reconsider the relationship between mind and matter. It challenges the materialist view that the universe is a purely mechanical system, governed by impersonal laws, and instead suggests that consciousness may be a fundamental aspect of reality itself. Whether or not we fully understand how consciousness interacts with the quantum world, it's clear that the observer effect invites us to rethink the very nature of existence. It hints at a reality that is far more interconnected, fluid, and participatory than we've ever imagined. And perhaps, as we continue to explore the quantum world, we'll uncover even more surprises about the relationship between consciousness, observation, and reality. So, as we conclude this exploration of quantum mechanics and the observer effect, let's remember one key lesson. Reality is not as fixed as we once thought. The universe is not a passive backdrop to our lives, but an active, evolving system in which we, as conscious observers, play an integral role. Our observations, our decisions, and our awareness shape the very fabric of reality. And in this way, we are not separate from the universe, but deeply intertwined with it. The quantum world teaches us that we are not just observers of reality, but co-creators of it. And that, in itself, is a profound and beautiful truth. Thank you once again. Good night.